Okay, folks, I'm going to guide you through some notes on page 38 about fission and fusion. They're pretty famous. You've heard of fission and fusion. You even learned about them in earth science, but you may not remember. Okay, here we go. Fission and fusion. They're both types of artificial transmutation. They're done by humans. They are both types of nuclear reactions. Okay, and we use both of these. Well, we use fission to produce energy and electricity nowadays. We hope to use fusion going forward. Okay, fission. It's a splitting of large nuclei. You start with a large nuclei and you break it into smaller nuclei. Fission produces large amounts of energy, like all nuclear reactions do. Okay? And that's a good thing. Fission produces large amounts of energy. The unfortunate thing about fission is that it creates radioactive waste or radioactive byproducts. You're left with radioactive isotopes that we can't really do very much with. They aren't terribly useful. We can't really easily reuse them as fuel. So that's a bad thing. Okay. Here's an example of fission. Okay. The standard fission reaction, we start with some uranium. Let me get my pen here. We start with uranium 235, and all uranium has its element number 92, so it has a charge of 92. And what do? We slam some neutrons into that. Okay, so here is uranium being slammed into with a neutron. You add these two things together. What do we get? Okay, well, the uranium breaks apart into a couple of different isotopes. We've got something with a mass of 92, and this is krypton, so it has a charge of 36. We also get another smaller particle with a mass of 141. Turns out this is barium that has a charge of 56. Barium is element number 56, so it has 56 protons. And in the end, we also emit 3 neutrons, okay, which can go off and can slam into more uranium atoms. And we get lots of energy. Okay? There's lots and lots and lots of energy. So this is how we create power in nuclear power plants today. We take uranium, slam neutrons into it, it breaks apart into these waste products, and in the process creates a bunch more neutrons which can go and slam into more uranium. So this is what we would call a chain reaction. We have to do this carefully because we start with slamming a neutron into some uranium. It creates those 2 byproducts, and it creates more neutrons. Those neutrons can go off and slam into more uranium and create more byproducts and more neutrons, and those neutrons go slam into more and more and more and more. And in this way, it is a chain reaction. But we have to be careful to control this chain reaction. Okay, so get those notes copied down. You do not have to do not try and draw all these diagrams of a fission reaction. Just understand that it is a contained chain reaction because these neutrons that are produced can go off and smash into more uranium atoms that are nearby. Oops, oh yeah, there's one more. Okay. Fusion. Okay, I'll explain to you a little bit more about how we control a fission reaction in just a moment. What do we want to know about fusion? It's the combining of small nuclei. In fission, we started with big nuclei. In fusion, we're combining small nuclei. And fusion happens in our sun. The fact that we are alive today is because of nuclear fusion happening in our sun to create heat and energy. Fusion produces large amounts of energy, like any kind of nuclear reaction, and that's a good thing. Hey, in fusion, there's no radioactive waste. That's a good thing, but it's very difficult to achieve. We haven't really figured out how to get fusion going and have it be continuous easily in our world today to power nuclear reactors, but it's pretty likely that we will get there before too long. Okay, an example of fusion. Okay, and again, we learned about this in earth science. We take 2 small nuclei, like some hydrogen 2. Okay, this is called deuterium. It's the special name for the isotope of hydrogen 2. We slam these 2 hydrogen atoms together, and what do we get? We get some helium atoms, and we get lots of energy. Okay? This produces lots and lots and lots of energy when we slam these 2 things together. Okay, now both fission and fusion have some things in common. They both release large amounts of energy, like any nuclear reaction. They both convert small amounts of mass into lots and lots of energy. That famous equation E equals mc squared means the amount of energy that you produce in a nuclear reaction equals the mass times the speed of light squared. That number there is a really big number. That means if you start with a small amount of mass, you end up with a very, very, very large amount of energy because the mass gets multiplied by the speed of light squared. These reactions produce way more energy than any kind of chemical reaction. Combustion, dissociation, single replacement, synthesis, decomposition, those are all rinky-dink and pathetic compared to fission and fusion. Nuclear reactions produce lots more energy than chemical reactions. And I want you to write down ME with a big star. Why? Because nuclear reactions convert mass to energy. They convert a little bit of mass into a lot of energy. It's all about me, folks. That's what you need to remember about nuclear reactions. It's all about me. They convert mass to energy. They start with mass. They turn it into energy. A small amount of mass becomes a very large amount of energy. Okay. In a nuclear power plant, really quickly, we've got this going on. Neutrons slamming into uranium atoms and creating some byproducts and creating more neutrons here. And those go off and slam into other uranium particles. Now, our uranium comes in the form of these pellets of uranium that we put into these bundles, which we call fuel rods, and then we kind of stack them in our fuel plant. How do we make sure that this happens in a controlled way? Well, we have a setup where these four things here, these are our uranium, these are our uranium over here, okay? And these green things that can move up and down, these are called control rods, okay? Here's off, here's on. Basically, if we put the control rods in, that blocks the neutrons from going and banging into lots and lots of uranium atoms, whereas when we lift the control rods out, the neutrons can bash into other uranium atoms and the fission reaction can proceed. So we bring the control rods in or out from between our fuel rods, and that allows us to control how much of the fission reaction is occurring, because the control rods will block these neutrons from banging into too many other uranium atoms. Okay, just in case you're curious. All right, very, very quickly, on page 43, you should memorize these particular isotopes: iodine-131, carbon-14 and carbon-12, uranium-238 and lead-206, cobalt-60 and technetium-99, and uranium-235 as a fuel and fission reactor. Write that one down. Memorize these. There probably will be a Regents question about at least one of these isotopes used by humans, and so there you go. Finally, benefits and risks of nuclear power. Then we're going to watch a good video. Benefits. Nuclear power creates huge amounts of energy. We don't need any fossil fuels, and we have less environmental impact, unlike fossil fuels, which can really create a lot of pollution. And it can be very safe when we are careful. It doesn't rely on weather conditions like drought or lack of wind can affect water power and wind power. But there are risks. We produce a lot of waste that needs to be stored or processed. There can be meltdowns and evacuations if we're not careful. These reactors can be very, very expensive to build. And there we go. And that is going to take you into a really good video about costs and benefits of nuclear power. Okay?